maybe for 10 years, we got a cloud computing center with the Air Force, and I'll be talking about that. The Air Force Cloud Center has been around for about 4 years, and what it's looking at for is assurance of clouds. I'll refer to a lot of problems, a lot of opportunities, and some work that we've done towards solving some of the challenges, but there's a huge amount of work to be done, and I think we're just on the tipping edge of a whole disruptive revolution in cloud computing, and I'll talk about that more if you're at the business section tomorrow. But this is a really exciting time, and I'm very envious of people who are much younger than I am, because this is going to probably define their lifetime. Research, the areas that can be done, and so on, are just absolutely tremendous. So I'm going to talk about, as I say, some results coming out of our work on ashore cloud computing. I'm going to refer to some of the things the IEEE is saying about cloud computing. And what you find is that, of course, cloud computing is evolving very much. So I've put it in the context where here's a project that we're doing on some of the problems we were trying to address, but then I'm going to refer back to some higher wisdom, if you like, the IEEE, and what it's been looking at with cloud computing and some of the issues that are rising that will certainly affect our project, and probably we won't be able to do very much about some of the issues. But these issues will be dominant in the next 10 years and will affect the way that people think about things. So our cloud center, we've got a lot of people, as you can see, and some of them are very well known. They're all working on trying to get an assured cloud computing internet. Well, to make assurances about cloud computing, now the problem that arises, the challenge is, although there are commercial systems that operate, and we have algorithms like PSOS and other types of consensus algorithms, we have big data tiered systems and so on, once again we're very enthusiastic about creating things. And just as in all cases, we don't worry too much about the security until it actually works. The result being that we have, if you like, exceeded perhaps some of our expectations in what we can achieve. And there are some questions one could start asking about cloud computing from a more sort of fundamental theoretical point of view, of whether they're actually doing the right things at the right time. And some of the research that's in our center is actually starting to look at that, and I'm very pleased about that. But it's going to be a big problem. It's going to take a long while to actually get there. And of course, it's very academic. Industry is not going to wait for us. They're going to go off and do their thing before we ever get to proving properties about big systems like this. So here's a sort of why the Air Force, why on earth would the US Air Force be worried about this? Well, they started off with a government directive saying that all governments should start using the cloud. And in typical sort of top-down manner, nobody actually knew what that meant in terms of the particular missions of the Air Force. I don't think they have a better idea now, but there's still lots of questions about it. But one thing's apparent, that these clouds actually form the basis for the future of computing. You're going to have two sorts of devices. You're going to have your mobiles and you're going to have your cloud. Your mobiles are going to be the way you sort of enter, look at all the data, all the analysis that comes from the cloud. Your cloud is going to be both pervasive everywhere, and it's going to have multiple vendors, and it's all going to be integrated and tied together in some way. And so you really have a very interesting facility, but now how do you use it if you want to, say, do some sort of mission? What sort of mission might you want to do? Well, let's suppose here is the South Pacific capital of Previa, and it's an island, and it's got a cure for infectious diseases, an advanced biomedical facility, whatever, and you've got a whole bunch of people at an opening ceremony You know, the United States Secretary of State, Directors for Disease Control, Director of the International Red Cross, and then all of a sudden you get news reports of an earthquake, a tsunami occurring, flooding, a tidal wave coming towards this place. What are you going to do? How do you coordinate rescue? How do you coordinate getting all of these important people to safety? What are you going to do? Now, it's likely that this is a big enough scale in such a remote area that you're going to use the Air Force, right? Because that's all there is. So then, what facilities can they use to do this? They would want, obviously, GIS systems. They would want systems about who lives where. They would want health systems and so on. They would want to be able to pick up and use some of the cloud that's normally used for, of course, daily occurrences, but they want to use it for the emergency services. How do you actually get everything to work? But they're also working in real time. I mean, this is something that's occurring, has disaster deadlines, if you like. You have real hard deadlines that you need to observe. Even with infectious diseases, you would have hard deadlines, because if you leave material around, unfortunately, people that have died around, you're going to get more diseases and more problems. So there are lots of deadlines and other things associated with this. You'd like real-time processing. But how do you do that on top of, well, say, cloud computing as we know it today? And the answer is, well, we don't really know how to use these systems that way. They were built for different purposes. This isn't one of them. But if you look at cloud computing as it's evolving, it's becoming more and more real time. For example, just sort of day trading is sort of motivating people to think about very, very responsive clouds. So there is a movement towards providing real-time systems, and they will have assurances, but we're not there yet. So to what extent can we make clouds assured? And that was the question the Air Force asked us to do. Here's some of the issues that I just mentioned, sort of things like, oh dear, that didn't work. I guess it's that button. All right, data transfer to the cloud, getting things to actually ship, especially under disaster. Computation in the cloud, trying to get that to work in real time. If you were going to do analysis of video of, let's say, satellite data and try and process it, huge amounts of satellite data, move your satellites over it and see what's going on. You would like to be able to retrieve all sorts of information that was already stored there and try and analyze what to do, like sort of, the height of all the land, businesses everywhere, the hospitals, or where people live. Basically, you've got a lot of different things all coming together. I don't know that Hadoop would actually do this, but what you've got is an interesting scenario that you would like to build out for. And of course, this could be anywhere in the world, so you would like to use anybody's cloud effectively. How could you do that? Could you virtualize your emergency plans and so on and just move them to whichever cloud is closer? Good question. Okay, so that's my sort of motivation for some of the research we've been doing, but it's in a broader context. The IEEE has put together a CS2022 cloud computing report, and it details all sorts of things that are going to happen in the next, however many of the years that is, 5, 6, 7 years, 8 years. But really sort of one of the things that's occurring is that as we're moving from a sort of data center with physical information on it and physical processing and so on to much more of a virtualized computing set of resources. And what we're applying is collective automation to those virtualized resources, and we actually manage all those resources automatically. And that affects our results. It affects performance. It affects the analysis that can occur. You're going to take a virtualized subset of compute storage, virtualized resources, and virtual connectivity, and you're going to manage it. Your application middleware service is going to be carved out. What you're going to create is a computing substrate, virtual computing substrate from all of this, and you're going to offer it to, well, in this case it would be the Air Force, but whoever you want to offer it to, in order to provide the facilities. And so that substrate becomes part of the network. So you're instantiating, if you like, a tremendous mechanism for doing something out of physical resources that are there, but you're using virtualization to be able to enable that. And then the question is, how do you schedule, how do you do the resource allocation, how do you do all these things in that type of context? And it becomes a very exciting, this is just a volatilized version of the previous thing. I was just wanting to emphasize, you've got the storage, the networking, and the programmability, and they're all virtualized. And they're all movable, they're all adaptable, they're all elastic. So just how do you build such systems? Very exciting. You can do this at various different levels depending upon how you use it. So now we're talking about infrastructure as a system, as a service rather. So you have a virtualized substrate of compute, storage, and connectivity resources, and they're making those available to the developer, and the developer develops stacks, right? Compute stacks to run on this from the hardware up. You can actually go and do metal servers in your IaaS. And if you look at Cloud Stack now, you have algorithms where you can package together bare metal stacks that you can pop on top of a cloud infrastructure and run, and you can specify how many of those you want and so on. You can also do it with virtual machines, and you can. The key thing is, how do you make this so cost effective that you can just have one or two people actually doing this and offload the labor to the people wanting to actually buy that service. And if you look at what AWS does, it's stepwise improved its facilities so that you can create your services on AWS very easily and incrementally. And that's not to say that there aren't other resources like Google and so on to do it. This is a very hot, trendy thing to be doing, and there's obviously huge economics in doing it. You're really building utility computing, and this is a major step. You can also do that at the program as a service level, and there it's very, very similar. And the question is, can you actually use the same tools in both cases? Can you use the same sort of interesting algorithms? This is providing your software as a service, where you're providing a whole complete support system, and of course you can repeat the whole mantra. It's the same issue. What you're going to turn over now is to the developer is a virtualized version of the workload and ask him to play with that. But it's still the same approach. All right. What is that meaning? Well, I'm going to reference a Gartner report that's talking about software-defined architecture. All of these things are actually based off an understanding, a much better understanding of how we build software these days. What you're doing is to build software architectures that can be adapted very, very fast and can be sold to huge numbers of clientele, to businesses. So you have, if you like, a software architecture that is open to being exploited by companies for lots and lots of different purposes. Why? Well, because you want to amortize the cost of your infrastructure, and you want to get lots of payback in terms of usage of your infrastructure, and lots of profit, obviously, for users of your infrastructure. So what people have done is to start building these systems to enable that. So you have app stores for your phones, for your mobiles. You have app stores for your networking. Now, if you go to software-defined networking, if you look at HP, it has an app store for OpenFlow. If you look at all these different applications, what they're tending to do is to place some sort of place to put your applications on top of an abstraction layer, an API that's very high up, that enables people to use these architectures for business purposes and to augment, if you like, the value of what you've built. So this is a key tool in how to do this. And underlying that is understanding how you build that layered architecture. And this layered architecture is that's emerged from OpenStack through AWS, through Eucalyptus, through all those different innovations, is kind of fundamental. Because up till very, very recently, we didn't do architectures like this. This is kind of novel. So I would say not only do you have a very interesting cloud design for utility computing, but you also have another way of looking at doing business, right? What you're trying to do is leverage the organization that you have in a cloud to create huge opportunities to provide economic stimulus, economic development, and employment. And that is going to be a huge driver in the next 20 years. So just hold on to your seats, become expert at this type of infrastructure, because you're going to be able to use it time and time again to create new businesses, new applications, and new money. All right, so we've talked about layered architectures. Now I'm going to talk about some research that we're doing just to sort of indicate what I'm meaning by layered architectures and the ways you can enhance things. So now I've sort of picked them from random from some of the things that my students and my colleagues are doing, because I want to just get over the nature, the flavor, and how fast everything's moving. So let's think about clouds, and we want to build schedulers for resources inside the clouds. How do we do it? There's a lot of different efforts. It's a very cutthroat area to do research in. One moment you think you've got the ultimate schedule, the next sort of Berkeley's come up with a different paper. This is fine, but it's the nature of things. It's because of the leveraging on the cloud infrastructure. So what is there to schedule? Well, there's a huge number of things to schedule in a cloud. You've got VMs, placement of virtual machines. You can place them in a transient manner. You can place them in a permanent manner. You have map-reduced jobs. You have things like Hive, SQL to MR jobs. You can place pig, right? It's pigs broken up into little Hadoop jobs. You can place those on the system. And, of course, you want to do optimization on where you place them so that they can get the data. You have map-reduce in many, many different forms. And you can have many mappers and many reducers. And the question is, how do you actually lay that out across an architecture, across a hardware? Distributed graph processing is coming effectively into its own. Social networking has made this an extremely profitable, interesting area, but there's lots of different organizations doing graph processing. There's lots of resources to be scheduled, and there's lots of schedulers you can build to optimize how you do that graph processing. So that's very cool. And then down here, we've got a big black hole, you might say, where you could drop huge amounts of effort because nobody really knows what they're doing. Well, they do know what they're doing, but they don't know how to do it. Machine learning and iterative algorithms just opens up a huge can of worms about how you would schedule resources. So machine learning right now uses huge big data memories. Well, if you look at what's happening, and I don't know, is anyone from HP here? No. So if I had some from HP, we could ask them about the machine, but essentially they're rethinking how you build these machine architectures so that you could use persistent RAM, well, it's persistent memory, to support large-scale computations. And if they actually succeed in doing that, machine learning will become much easier because you'll have the memory that you need to be able to do this type of operation. And of course, there will still be a question of scheduling. So we're on a verge, if you like, of moving to a whole different level of using these machines, thinking about these machines, and resource scheduling is going to be one of the key issues about what to do. So, what can we think about as we look at this? This is just continuing the same statement before. There's MPI algorithms, if you're into scientific computing, which U of I is. If you're into real-time processing or genetics or whatever, there's also the Spark efforts by Berkeley. There's a Sharp, which is similar to Hive. There's D-streams coming out of Spark, which is how you schedule streaming data. Now, if you go to Yahoo, you'll find Storm for streaming data. If you go to the Berkeley, you find D-streams. but it's still going to be the same questions about how do you schedule these things, how do you operate these things. Typically, D streams, well, they're kind of cheating. They break up the D streams into micro batches, and they schedule the micro batches. FIFO, over 100 millisecond window data input, and that turns out to be nice and effective, but it's not the ultimate. So, typical to resource scheduling, you have a bunch of constraints. You have MapReduce data locality. You want to make things highly available, and that could interact with what you're doing with scheduling. On MPI, you have gang scheduling needs. You want to have everything start up and finish at the same time to reduce jitter and all those other nasty consequences. In a real-time system, you've got network delays, and that really causes you a problem because networks are stochastic and they don't ever finish at the right moment, so you have to sort of time everything and be very careful. These streams, well, an issue is how do you quickly place these things and get them to run, and what's the network substrate inside the cluster do you use to provide those D streams. So lots of scheduling issues. Here's Hadoop. Hadoop as a resource manager. The Hadoop resource manager knows about various things. It knows about all of the resources here, and then you supply a long list of MapReduce jobs, and what it's going to try and do is take that and any other jobs that's being scheduled, and it's going to try and generate jobs for these machines. Now this pig task, for example, could create 50 map tasks, 20 reduced tasks, and maybe there's 2 jobs here. Another one's output is to generate 12 maps and 3 reducers, and you would like to map it onto this architecture. Maybe you've got 10,000 nodes and you've got lots of these peak tasks and you'd like to schedule them. But that's not all you'd like to do. If you look at what Yahoo's job task schedule looks like, they mix together tasks from Hadoop, from other places, and so it's a mixed input here. They have Hive tasks that are coming into the system, and those need to be mapped. They have other custom MapReduce jobs, and those need to be mapped. So you get a very complicated sort of looking scenario, and as you move towards a more time-shared operation of the system, multi-tenancy is what they call it, what you're looking at is much more complicated scheduling. So we have some limitations. Mostly things are restricted, they're one of a kind. Other frameworks can't benefit from one particular sort of resource manager. The resource managers are separated into different buckets, if you like, smokestacks, and that's no good. There's complexity to add additional frameworks. The resource manager would have to contain all the placement logic and so on. It doesn't operate together. It's not very cloud-like. We need to change it, right? So we need to change those schedulers. Now there's been some attempts to do that. The latest is to go to Yarn for MapReduce out of Yahoo. Google does something else. And in this Yarn resource manager, what you're doing is having Yarn jobs come in, and then they're scheduled. But the Yarn is a distributed system where it actually has an app manager managing jobs of type A on these systems. And so this would actually take those, map them across. Then if you get a different type of set of jobs, you would have a different manager, and that would schedule those jobs. And if you have yet more, you would do the same thing. Now there's an issue about getting all the data to the right manager and actually sharing the state of the whole system across all those nodes. And so there's a very complicated architecture of notifying people and keep alives and so on to do that. But what you notice about this is it's very hierarchical, and it's sort of one level, and it doesn't distribute control very well over everything. So here's some benefits. Application masters contain application-specific logic, so it's easier to maintain. The benefit of having a cluster-wide scheduler for many kinds of jobs. You have global cluster knowledge, can easily program in constraints such as gang scheduling, data location, and other job requirements. It looks a bit like that if you look at the diagram in Yarn. So you have your node managers down here. You have the data being fed down to these about the state. You have your resource manager up here, which takes jobs and allocates them to the node managers. And that is kind of certainly where Yahoo is at the moment. So issues, well, how do you take this and scale out with MapReduce? The problem is that the Yarn system, that centralized system, doesn't scale very well beyond 10,000 nodes. So if you're building a really large machine, you've got a problem. Why do we need a centralized scheduler? Why couldn't it be a distributed one? Well, that's because we know how to build centralized schedulers. We don't know how to build distributed ones. We need some better sort of technologies. What about global policies over all of these systems? Limits of a centralized scheduler. Well, you remember D-streams, Spark. That's got a sort of centralized way of doing things. But what they've done is to weaken that with Sparrow to try and achieve more of a distributed system. However, if you're going down this route, this centralized scheduler system, you have a single point of failure, which takes a long time to recover from. You should be able to have more machines and more scheduling decisions made in a sort of scalable way without having to, create something totally new. So there's overall a big problem with this. So if you look at all of the goals and assumptions, you want a hierarchical architecture for the scheduling purposes. You need high throughput, you need long-running workers, you need to have send task description. You don't want to create workers on the fly because that's expensive, right? So you'd like to have schedulers that are long-running. You'd like less features for performance. You'd like contributions from batch scheduling, late binding, and all these other things into that system. How are you going to do it? So if you look at a time scale, in 2004 we were quite happy with 10-minute scheduling for MapReduce jobs. If you now look at Hive, well, it got it down to 209 to schedule a query. Dremel queries was sort of down in 10 seconds. In 2012, Impala was sort of moving towards the millisecond. If you do things in memory, like the RAM projects down in Berkeley, you're getting close to 100 milliseconds. The Spark queries are down there. But if you sort of want to operate, say you want to operate between exchanges doing trading, day trade, instant trading between different on the stock markets, you want to be down at at the 1 millisecond level, right? Now, the same thing for the Air Force, because they would like to be down at 1 millisecond level, then they feel confident they could do things. So there's a continued pressure to try and make this faster and faster and faster. How do you do it? Well, what you're going to do is to spread your decision making. You're going to make long-scale decisions in your more centralized, more knowledgeable schedulers. You're going to have schedulers that are very local that can make very fast decisions, and you're going to allocate things in such a way that you can make really fast decisions about the thing that you need to make fast decisions about. So we need to exploit that nature, the nature of locality, in the way we build these schedulers. So here's an example. This is taken from Sparrow. What happens is the scheduler actually randomly picks a couple of workers to run the Sparrow jobs on. And what it does, it just tosses a coin, effectively, so it's very fast. And then it tries that. And it hopes that one of the workers is actually successful. All right? And if it goes, you can set Sparrow to operate with 2 or 4 or 8 or whatever, but actually 2 works fairly successfully. And that's kind of interesting. So this is the layout for Sparrow. What happens is you have a scheduler, it allocates workers to the Sparrow node monitors, and then these guys go and choose a couple of machines to run the jobs on. Well, that brings us to what Google has pioneered and what now is cropping up in OpenStack, which is to build schedulers that sort of mimic and exploit what's happening with Yarn and what's happening in the nature of things. So you're getting 2-level design schedulers. where you offer particular resources to individual schedulers and you accept reject offers at scheduler level. And this nature of doing things has become, well, there's a system called Omega that's in the Google environment. Mesos is the Apache version of it. So what it looks like is something like this. There's a Mesos master scheduler, and it has all bunches of slaves that do MPI execution or Hadoop execution and so on. It has standbys. It tries to keep all this intact using eventual consistency using Zookeeper. So you've got a very complicated ecosystem being developed, and these things can be tailored for sort of real-time scheduling and response needs. Now, is this satisfactory? Well, no. There are missing factors of this. A big sort of issue that comes up is real-time scheduling and stream scheduling. How does that impact these systems? So here's how you would actually go about doing things with Mesos, and I'm not going to detail it, but I'm going to say, well, Mesos has great properties. It's no blocking a job, doesn't block on job queues, easily maintainable, offers can be filtered, provides speed up, but it's kind of pessimistic because actually it assumes schedulers will have conflict, so it doesn't do the schedules which would cause conflict. It has a lack of knowledge. The schedulers have a lack of view of what's happening in the cluster, and it's possible that better decisions could be made. Omega, which is the Google implementation, looks a bit like this, and it actually has transaction state for distributing knowledge about the cluster to all of the nodes so it can make better decisions. Now, these things still don't run the streaming data, the D streams, or whatever you want to have, the real-time processing streams that we need for cloud applications to real-time data. Of course, you can see where I'm coming from for the Air Force. So can we extend some of these notions? What is the right architecture for these schedulers that would allow us to go into a much better systems? So you need to share system state. You need multiple instances of the same type of scheduler. You could have a sort of combination of Sparrow plus Omega to make this really fast. You need some formalism, some design patterns. Question is, how far away are we from actually getting this to really work? Well, we've got wrappers and things like that for deployment with Docker. And Mesos already uses Linux containers, so you can actually use lightweight scheduling and resource allocation to operate things. This is different from Yarn. Yarn uses C groups. Trying to get these to work together is an interesting question. But we need to move forward on this and move to another level, if you like, of what we're doing. So I won't talk about that because we've discussed that. What do I want to finish up with? I might as well finish up with something fun. So I'm just going to finish up and say most of these schemes don't actually have verification that they work. So if you look at PSOC, there is a proof that Pesos works, but if you look at deployments of these things, Zookeeper and so on, there are no real sort of proofs that actual implementations function in the way that they're functioning. We're talking about scheduling here. Let's stick to one topic. Okay, so I talk about scheduling. But when you've got these things, there's no proof that, for example, consensus, eventual consistency actually operates. And in fact, in some of the checking that we've been doing, and I won't go through this because it would be terrible, but there's a CAP theorem that says, well, you can't have transactions if you have a big enough system. And, okay, if you don't have CAP, you have eventual consistency, and there's eventual consistency routines, and they're tremendously difficult to understand. And if you put them on top of networking and everything else, they're even more complicated. Well, it turns out that in certain cases, we found inconsistencies. So if you're running... So a lot of these schemes allow you to use different eventual consistency. It turns out that the eventual consistencies aren't consistent with each other. And if you actually run them simultaneously, you can produce problems inside the system. How do we know? Well, we ran modeling to find out. All right? So there is a huge amount to be done in this area of scheduling. One of them would be to actually verify all the wonderful systems that we're trying to build, including the ones I'm thinking about building. We don't know how to handle real-time scheduling in these large cloud systems, so that's a real problem. There is, goodness knows, how many opportunities for everyone to write papers, get proposals, do some really good contributive research. So I'm going to finish at this point, and this is just a diagram of all the things it doesn't actually do. They're X's, and the things it does do that we can show are ticked. But basically there are some problems in these systems, and I would recommend you looking at those as a good sort of place to find PhD topics. So, I'm not going to bother with that. I was going to talk about those, but I've run out of time. So why don't I just finish with questions? If you've got questions, I would love to. Well, you see, I've got lots of slides. I'm very good at having slides, and I'm not going to talk about them all. But I was going to let you ask